Hi everyone. What we're going to do for this first lecture is basically have a quick recap of, the philosophy of chemistry and, do a bit of Chemistry 101 review, because Chemistry 102 is a second class in sequence and it relies entirely upon a good foundation in Chemistry 101. Okay, so if you're a little bit rusty on Chemistry 101, this is for you, but it's good for everybody just to kind of brush up on the tools, what you need to succeed in 102. All right, so a little bit of philosophy first, just to get us back thinking like chemists. Maybe it's been a while since we took 101, and once we got through some simpler background stuff, then we'll move on to the 101 review itself. Okay, now what I want you to do, now remember how this works, right? There's lots of gaps in the notes, and I really want you to kind of pause when I say pause and fill out the appropriate piece of work on the paper in front of you, right? It really pays to print this, have it ready to go, before you even watch the video. Okay, so hopefully, if you haven't got the stuff printed in front of you, pause me now, go get it, right? Okay, all right. Are you back? Okay, so let's take a look. So first question is kind of philosophical. All right, we're going to be studying chemistry, right? But did you ever really think what chemistry actually is? Okay, what is chemistry? Okay, so the first question, here it is. So in your own words, describe what you consider chemistry to be, or if you want to look at it from kind of a different perspective, what you think the job of a chemist is, because a chemist does chemistry, right? So, pause me now, write down what you think chemistry actually is, and then we'll go back and look at some answers. Okay. All right, you back? So, maybe you put some chemistry words up here like, study of elements, study of compounds, do experiments, things like that. Those are all good, but it's not really the words themselves that are important, it's how they link together. Okay, and that kind of fits in what I call the official definition of what chemistry is. Now, the official definition, if you like, is something you can just pick up by reading the book, or if you're like me, you just read a bunch of chemistry books and kind of combine them all to come up with an equation, sentence, right? Sentence or two, a definition. All right. So very simply, and I'm English, so I like long sentences with commas, right? So very simply, chemistry is the study of matter. Okay, we'll talk about what matter is strictly defined as in a moment, but I think you probably know what that is. All right, so chemistry is the study of matter and its properties. Now, you may remember from, and I'll underline important words here. You may remember from Chemistry 101 or maybe Chemistry 100 that matter has two kinds of properties, right? They're either chemical, which is to do with changing into something new, a non-reversible process, or physical, like boiling and freezing, which are reversible processes, or just as-is properties like color or something. Okay, so we're primarily going to concentrate on chemical properties, but be aware that matter is often defined by its physical properties. So, for example, water is a clear colorless liquid that boils at 100 degrees C. It's the only clear colorless liquid that boils at 100 degrees C. Sure, there's lots of clear colorless liquids out there, but then, when you go through the list of physical properties, it defines the matter, right, or the compound in this case. Okay, so chemistry is the study of matter and its properties, the changes matter undergoes. Primarily we're thinking about reactions there, but condensation, freezing, they're also changes, but they're physical. We're primarily interested, I should say, rather, in changes that are permanent, so chemical reactions, right? And if you think about it, whenever you do a chemical reaction, heat goes out or heat goes in, that's thermodynamics. And the energy associated, move this up, with those changes. So just to read it, sorry, a bit of a technical issue there. Okay, so back to the definition. Chemistry is the study of matter and its properties. chemical and physical are both types of property. The changes matter undergoes, aka reactions, and the energy associated with those changes or reactions. Okay, so hopefully you picked up a few of these words in your own definition of what chemistry was. Okay, you may have been more specific, that's okay. We'll get into the nuts and bolts of how matter is arranged in a little bit. Okay, all right. Now, also interestingly, for Chemistry 102, we do a lot more on the energy component. Okay, so thermodynamics, we'll look at that in much more detail. We did a little bit of that in 101 with Hess's law, but we're going to build on that and do much more detail. Okay. Now, key words then. Oh. So matter, of course, is stuff, okay, to use a street definition, okay? And stuff is anything with mass and volume. For example, this pen is a piece of matter, isn't it, right? Because it has a defined mass, I can feel weight in my hand right under gravity. And it has a defined volume, I can feel its shape in my hand, okay? So matter is anything with mass and volume. So chemistry is the study of matter, so hang on a minute, that's a big list, right? So if you think about it, anything with mass and volume, any physical object can be studied by chemistry, right? So that would be a big list. So the trick is not to think about what chemistry can study. It's kind of the opposite. Try and think about what chemistry can't study, and that kind of gives you, by default, what's left is what we can look at, okay? So a question I have for you, and feel free to pause and think about it, is, can you think of anything without mass and volume? Obviously, Britney Spears' head. That's a joke. Right? But, can you think about anything without mass and volume? That would be off the table for a chemist, right? Give you a second. Think about it. Pause me, come back. All right. So, things that come to mind are thoughts and ideas. Philosophy, in other words, right? What does Christianity weigh? Right, it's just a concept, right? So you can't weigh that. It has no mass, has no volume, right? Okay. So, thoughts and ideas, philosophies, things like that. What does communism weigh? Socialism. Evil socialism. What do those things weigh, right? Nothing. So they, their thoughts and ideas, they can't really be studied by chemistry. Can you get it in a test tube? No. All right. Other ones, kind of a little bit more esoteric, perhaps. Well, maybe not. What about, let's give you a hint. Time, right? How much does a second weigh? What's the volume of a second? Well, we can't measure them in terms of mass and volume, but we can measure them, in other ways. And they do come into our experiments, particularly when we do kinetics, when we see the rate of change of something with time. So we need time as a variable. But time itself, as an independent thing, is not something we would study. You leave that to the Stephen Hawkings of the world, right? Okay. Other things? Well, energy. Can you go to the store and buy a jar of calories? Well, no, because they're units of measurement for energy. Okay, energy can't be kind of stored, really. Okay, it can be exchanged. That's what the sun does with us right now and has been doing for billions of years, right? Okay, energy comes from the sun to us, all right? But we can't kind of keep that energy in a jar. We can transform it to different types. So solar panel turns solar energy into electricity, for example, all right? Okay, but we can't really store pure energy, all right? Okay. Anything else? Good question, right? Some people say, oh, outer space, right? Outer space definitely has space. It says volume, but does it have any mass? Well, the answer is yes, it does have mass. If you are a big fan of, the Stephen Hawking type physics, particle physics, if you actually remove all the air from a container and try and make a pure vacuum, subatomic particles begin to appear and disappear, okay? This is kind of thought to be the origin of dark energy, because these things make a pressure, right? Okay, so the emptier space gets, the more pressure it makes, and this is what's forcing the, personal opinion, forcing the galaxies apart faster than we calculate. Dark energy, dark matter. Okay, so, space is not empty, so it's not, off the table. It still contains a small amount of mass and definitely has volume. Now, extra credit. Friday, the deadline for this work. Can you think of anything else without mass and volume? Okay, think about it. All right, now, Moving on, as we know from just, probably from high school, there are 3 states of matter, or I should say, stable states of matter, right? Okay. You know what they are. They are, of course, and this is kind of simplistic, but solid, liquid, and gas, right? Okay, now, obviously, those states of matter are stable because you can kind of put them in a jar, come back tomorrow, and they'll still be there, right? Assuming the temperature is in the range where they're solid, liquid, or gas, right? Okay, are there any more? Are there any more states of matter? Well, there's several more states of matter, actually, okay? The one that's most common is plasma. Plasma's not stable, though, okay? So are these kind of weird, kind of supercritical liquids physicists make all the time, but things that are technically defined as their own states of matter, like plasma, but they're not stable, okay? So if you own a plasma TV, you can make plasma, right? So you turn your TV on, it gets bright all of a sudden. That's because in those little kind of ampules, which are the dots on your TV screen, there's some gas at a low pressure. And then the electrodes kind of electrify the gas, provide it with a lot of energy, and the gas is basically destroyed. It turns into atoms, ions, electrons, right? And that kind of soup of particles emits a lot of light. So plasma is not stable because you can't store it, okay? If you turn the TV off, it goes dark, right? Why? Because the plasma went away, all right? So the sun's surface is plasma, a flame is plasma, right? So you maybe heard if you're into welding, plasma cutters, right? So really, flames, really bright, hot flames. Okay, so plasma is the 4th state of matter, but it's not stable, so we don't really consider it too much in a chemistry course. Chemistry is a very practical subject, right? If we can make it in a test tube, we're interested, right? And so, we kind of limit ourselves to the states of matter that are stable. So solid, subscript S after a formula. So for example, if I had a gold bar, it's AUS, right? Okay. Liquid, subscript L. Glass of water would be H2O liquid. And finally gas, nitrogen's in the atmosphere and 71%. There we go, nitrogen gas, all right? So these are chemical formulas, which we'll talk about more in a bit. And these are states of matter. It's a bit like dotting I's and crossing T's when you write equations. You should always include state symbols for every formula, all right? Now, interesting question. What's matter made from? Okay. Now, again, when we think about this, we like to think like chemists, okay? So we think stable, all right? So what are the stable building blocks of matter, all right? Well, it's the classic idea, right? So back in the day, Democritus, right, famous Greek philosopher, did a thought experiment. And he said, take a piece of matter, and you can do this thought experiment right now. Take a piece of matter, and in your mind you're thinking about it, just cut it in half, right? And then take the half that's left, cut it in half, right? Half that's left, cut it in half. And his question was a simple one. Can I just keep cutting this thing in half forever and having a smaller piece of matter each time? Or do I get to the point where I can't cut it in half anymore? Okay, so the question was, is matter infinitely divisible, or do you get to the point where you can't cut it anymore? Therefore, if you think about it, that would be the smallest stable piece of matter, because if you could cut that in half, it wouldn't be stable, right? So the answer is you do get to a point where you can't cut it in half anymore, yeah? And we now know those smallest pieces of stable matter as atoms. Now, atoms comes from the Greek atomos, which means uncuttable, okay? That's where the word atom comes from. It means the uncuttable small piece of matter, right? Okay, which is the atom. Now, tell me about atoms, right? If you look in your periodic table, about 112 different types of atoms. They usually, we like to envision them as these small spheres, typically between 0.1 to 0.9 nanometers wide, okay? And I like to think of these as nature's Legos, okay? So think of the periodic table a bit like a giant, you ever go to Subway, you see the little containers with the little, with the tomatoes and the onions and all that. Think of a giant Subway counter with all these little kind of containers, 112 containers. And inside each container, there are these little spheres, right? Each of those are atoms of a particular type. That's how I like to envision the periodic table, as just a big Lego set. Then if I want to make something, if I want to make water, for example, I take an H, take an H, take an O, stick them together to make H2O. And that's really how nature works, all right? So nature is so diverse because there are 112 different types of atoms, yeah? So think of the possible combinations. And a nice way to think about that is, well, 26 letters in the English alphabet, right? And I probably get 250 combinations of those we call words. So from 26 characters, I get 250,000 valid combinations. Hey, nature's alphabet's 112 characters. Imagine how many valid combinations there are. And then those, once they're valid, we write them down, they become formulas. It's kind of interesting, right? So 112 types of atom, which combine in different ways to make elements and compounds. Question. Can you see atoms? Well, the answer is no, not with a microscope at least. Okay, so you can't see atoms with a microscope because they're too darn small. All right. Now, way to explain this is to think about a movie. Okay, one of my favorite movies is The Perfect Storm. Right, and if you've ever seen The Perfect Storm, maybe I'll show you a picture here, there, wherever. Okay, show you a picture of the movie poster, essentially, right? And it's basically a picture that looks like this, right? So here's a giant wave, and here's a tiny fishing boat. And the tiny fishing boat gets crushed by the wave, and George Clooney and all his friends die, right? Okay, it's a true story. It's based out of Gloucester, Massachusetts. Okay, now, why did the tiny fishing boat get destroyed by the big wave? Because the wave was too big, essentially, to interact with the fishing boat. If you have a really big boat, it's of the order of the size of the wave or bigger, it will interact with it. It will float on top and go up and down with the wave, right? But if the particle is too small, the wave will just not see it and just go straight over the top, okay? And this is what we see with matter. If you try and look at an atom with a light wave, which is a regular microscope, the wavelength is probably, 500 nanometers or something, visible light. An atom, as we said, is 0.1 nanometers wide, so it just doesn't interact with that matter that's so small. All right, so when it comes down to it, you probably have to have a few thousand atoms wide structure to see it with a microscope. And then you get into all those cool pictures you see in biology of cell membranes and stuff. That's kind of that order, right? Okay, so you can't see atoms with visible light because the wavelength's too big. And you say, oh, wait a minute, there's something called an electron microscope. And yes, there is. You can get an electron microscope, and essentially you can make electrons act as waves and have a shorter wavelength. Fantastic, okay? And you can see things with an electron microscope. So look at these electron microscope images. You see them, right? Maybe 100 atoms wide structures, right? Okay, again, there is a finite limit. The wavelength's shorter. So you can see smaller things, but there is a finite limit, okay? Now, probably 100 atoms, right? But you can, the more energy you give the electrons, the shorter the wavelength. But it gets to the point where you give them so much energy, they just basically punch through like projectiles. So there is a limit to electron microscope resolution, all right? So the question is, well, how do I then rationalize pictures like this, okay? So these are images of actual atoms in nature. Okay, how does that work? Right, so I'm going to skip ahead a little bit, and it all comes back to a very famous experiment done about 1984 by Binning and Ruhr. Okay, now they understood that you can't see atoms below the wavelength of the light or electrons, whatever you're using to try and image them, right? And they just went back to the basics, and they said, well, think about this. Think about how like an old-style record player works, right? How does an old-style record player work? Well, you have a big vinyl disc, right, with grooves in it, yeah, okay? And, good Trivial Pursuit question, how many grooves are on a record? Well, there's actually two, one on the front, one on the back. It's just like a concentric circle, goes out like that, right? Okay, so it looks like loads of them, but you put the needle on the record and it spins around and eventually gets to the middle because there's one groove. And then inside these grooves, there are little bumps, right? So the record spins at a certain speed, RPM, 33, 45, whatever it is, right? Okay. And then when the needle, because you put the needle on the record, the needle goes over a bump, it deflects up, moves a magnet, inside the speaker makes a sound. So you're translating geographical information, which is the bumps in the groove on the record, into sound information. So you're translating geographical into sound information. Okay, fair enough. Why am I telling you this? Because you can miniaturize that, okay? You can get an atomically flat surface, and that's a picture of an atomically flat surface, right? And then you can put larger atoms on that surface, freeze them down to, you know, liquid helium temperatures 4 Kelvin, and they'll just freeze in place, okay? Then you can actually get an atomically sharp tip, and say these are atoms on the surface now, they'll ride over the top of those atoms, because on the outside of every atom there's electrons and they repel, right? So they'll ride over the top. And that's the origin of what's called STM, that scanning tunneling microscope, which are these pictures, or new AFM, which is more like the stylus of a record. All right, fantastic. All right, so it's a bit like, you know, a very miniature record player. All right, now, in the 1990s in Alameda, California, at the IBM lab, surprise, surprise, what they decided to do was have a game of soccer. So they actually got the tip, having mapped where the atoms are on the surface, right? They got the tip and lowered it down and started literally kicking the atoms around on the surface. And they were able to move individual atoms around on the surface. That's how you're able to get images like this. This is not a picture. This is a geography map. These colors are just added later, okay? So they move 1, 2, 3, 4, 5 atoms high, 3 atoms wide to make letters here, okay? So IBM is the smallest ever logo there. It's like 5 atoms high. Okay, you can put them in a circle, you can put them in a cylinder, and again, as I mentioned, that's the surface. If you want to look for a search on Google, IBM image, STM image, right? You'll get to their site eventually, and there's a gallery. Okay, you can look at all these images in a gallery, which is really cool. All right, so that's kind of neat, but what about the practicality of it? Okay, so in terms of a practical thing, all right, what I'm going to do is show you the matter flowchart, how this pen can be broken down into its individual components in a systematic way, which will allow us to kind of examine matter in more detail, okay? So this is probably something you remember from before. But matter that's pure, and there's a nice little trick. If you have pure matter, it always has a formula, okay? So if I have a glass of water, I just say, as a chemist, H2O liquid, right? Because all the particles are the same, these little H2O molecules, and they're in this container, okay? So pure matter on the macroscopic level, a gold bar, Au solid, right? Okay? Glass of water, H2O liquid. If it's just one type of particle in the space there, it's said to be pure, and it has a formula, so those are synonymous terms, all right? Something that's impure, maybe it's oil and water, right? It's a mixture, and then we don't classify it with a formula, right? But anyway, we're just talking about pure matter, right? So pure matter can be classified as either an element or a compound, right? That's true, isn't it? Yeah. So what's the difference? Well, elements are matter made from one type of atom. Compounds are matter made from different types of atom in a fixed ratio. So for example, if we do a few examples, Au solid is a gold bar, N2 gas is also an element, right? Because it's 2 nitrogen atoms which are the same stuck together. Just because it's a molecule, that doesn't determine if it's an element or a compound, it just determines its size. Size is irrelevant when we talk about definitions of element and compound. Compounds, maybe NaCl is a good one, salt crystals, and maybe H2O again. Okay. All right. Different types of atoms in a fixed ratio. All right. 1 Na, 1 Cl for sodium chloride, 2 H's, 1 O for water. Fair enough. So matter fundamentally is defined as an element or a compound based on its formula. Same atoms, element, different atoms in a fixed ratio compound. Then we get into 2 important words, right? Giant and molecular. Again, giant and molecular. What's this about? It's basically a macroscopic definition based on size, right? So a giant element is literally something you could hold in your hand. Molecular is made of molecules, a few atoms stuck together. That's the definition of a molecule, right? Too small to see with your eye, right? So a giant element is a gold bar, for example, using our list here. Or maybe a diamond, which is just carbon, solid, right? A molecular element might be N2 or O2 or H2, okay? That's a molecule of just two atoms, right? Now, maybe saying, well, why does the giant element just have the one symbol, right? There may be 10 trillion atoms of gold in a gold bar, but we can't count them, and gold bars are different sizes, right? So we just use the lowest kind of ratio, if you like, which is called the empirical formula. So, you know, whenever you see Au solid, you know it's giant because you know gold, right? And you know diamond is carbon solid, right? So we don't write the actual number for a giant. We just do the lowest ratio, if you like. There's a 1 there. Yeah. But for molecules, yeah, we tell you the actual number and type of atoms in a piece of matter, the molecule. Similarly, sodium chloride is a giant compound. NaCl build a giant salt crystal. It might be 10 trillion Na, 10 trillion Cl, right? But we don't write that. We just write the lowest ratio, the empirical formula. Molecular formula is molecular formula. It's different. It's the actual number. So there's 2 H's and an O in water. Maybe it's CO2, carbon, and 2 oxygens. Fair enough. All right. Now, fundamentally, what are these things all made from? Right? I'm going to kind of do something kind of weird here. Molecular, I'm going to write it there. All right. Fundamentally, all these things are made from atoms. Okay, think about Nature's Subway, as I mentioned earlier, right? Say you worked at Nature's Subway and someone came and said, I want a gold bar. You just reach into the gold bucket 10 trillion times, stick all the gold atoms together, and you make a gold bar, right? So giant elements are easy, right? Molecular elements are even easier. It's oxygen day, right? What do? Get an O, stick them together. Would you like to make that a meal, right? So fundamentally, atoms taken from the same box, stuck together, make an element. Molecular elements, just a couple maybe. These are all diatomics, but there are triatomics sometimes. Okay, and these are just loads of the same atom, right? Okay. Now, if I want to make a molecule, say it's water day, take an H, take an H, take an O, right? So molecules are also made from atoms in a fixed ratio. Now, why did I kind of do that? Because I wanted to leave a little space here, okay? Ions. You may remember this from 101, but giant compounds are essentially always made from ions, okay? And ions themselves are either atoms or molecules that become plus and minus, and then those plus and minuses stick together. So if I take an atom of Na, make it plus, an atom of Cl, make it minus, they stick together, okay? So ions can be made from atoms, right? So Na and Cl are atomic ions. But ions can also be made from molecules. You've seen ammonium, it's a molecule with a charge NH4, whole thing plus 1, right? Or NO3 minus, whole thing minus 1, all right? So let's write a few ions there. NO3 minus is a molecular ion. Na plus, for example, is an atomic ion. All right, so we make them into atoms and molecules, and then we give them charge, right? And those charged particles stick together. Yes, I can stick an atomic ion H plus with a molecular ion NO3 minus, nitric acid. Okay, now I'm going to pause there because I'm about to run out of time. See you in a second. All right, that's a pretty good place to stop because we just got to the point where the Greeks stopped, right? So everything is made from atoms, the smallest indivisible or smallest stable particle. And anything in the realm of an atom or bigger is really chemistry, okay? But you know for sure, just from high school and watching TV, there are things smaller than atoms. Those are called subatomic, right? Sub, smaller than. And that's really the realm of physics, all right? So we have these things called particle physicists up at Fermilab, you know, they're always discovering interesting and new particles, right? Okay, so if I take an atom and I break it into bits, which I can do, right? But the bits just won't be stable. They won't be able to be stored, okay? So, you know, we can make them for a second and they kind of disappear or make stable matter themselves, right? So it turns out that, you know, if we think about an atom, what is an atom made from? If we have our classic picture in our head, there's this little pip in the center and these things whizzing around, right? And there's kind of the perimeter of the atom, okay? So we have a bunch of subatomic particles. We have electrons, which are the things whizzing around, of course, and if you like, orbiting a nucleus. Okay, so the nucleus is in the center, the electrons are whizzing around. All right. An electron actually is one of the 17 fundamental particles of nature. There's something called the Standard Model of Nature, or Standard Particle Model. It's the list of subatomic particles that the universe is made from, okay? And they kind of all link together to make matter, okay? So the nucleus itself is not a fundamental particle. It's made of other things. There's protons and neutrons, okay? So there are plus charges in the nucleus and then neutral charges in the nucleus, okay? Approximately equal numbers of each for light atoms. So for example, carbon, as you remember, typically weighs 12 AMU, 6 protons and 6 neutrons, so the most stable form of carbon, okay? Protons themselves and neutrons are not fundamental particles. They're made from quarks. Extra credit. Which 3 quarks make up a proton? Email me by Friday. Okay. Those are actually, the quarks were actually discovered in the 1960s at Fermilab. I think the famous top quark, which is the most important one, was discovered at Fermilab in the 60s. All right. So, you know, there are obviously more fundamental particles, but we'll leave that for a physics class. All right. Now, we can use our flowchart, okay, so kind of keep this on the side and just follow through as we do it, maybe, okay? So maybe I'll try and do that, all right? So what is water made from? How do you know? All right, well, water has the formula H2O, right? That's the formula of liquid water, isn't it, right? And if you think about that, and there's a water molecule. Now, I don't like these pictures, right? Because once, you know, I take my H, it's nature's submarine, right? Take my H, take my O, I weld them together permanently, right? So they actually look like a new blob of matter, like almost like a little jelly bean. Yeah, if you look at a water molecule under STM, it looks like a jelly bean because it's become this new independent thing, right? So, you know, obviously that's an O, an H, and an H. It's no longer got anything to do with what it was made from. If you think about it, hydrogen and oxygen are flammable things, right? Water puts fires out, so it's a new material with new properties. Okay, so, but hey, we can only really describe it by what's inside. It's a bit like, you know, when you see a minivan go down the street, you say, oh look, there goes a minivan. That's human brain, right? You don't say, oh look, there goes an aluminum tube with 2 kids and a mum in it, right? But that's how a chemist would explain it. We have to explain that new piece of matter, not in terms of its new properties or anything, but what in terms of what it's made from, okay? Which is kind of weird, all right? But remember, molecules have different physical and chemical properties than the things they're made from, but we explain them or name them in terms of what's inside, hence the origin of this, right? Okay, so that's an H, an O, and an H all stuck together forever. Okay, now, question is, how many molecules would make up a drop of water? Try and just think about that for a second. You know, tell me when to stop. You think it's 1,000? No, obviously not, right? Million? No. Billion? No. Trillion? No. There's your stimulus package, right? 3, 6, 9, 12 zeros. 15 zeros, 1,000 trillion? No. 18 zeros, million trillion? No. 21 zeros. 3, 6, 9, 12, 15, 18, 21 molecules in one drop. Now, that's interesting, right? That shows you the scale between macro and micro. A drop of water is a microscopic object, too small to see. Sorry, a molecule of water is microscopic, too small to see. A drop is macroscopic. Okay, the size scale is immense. Okay, all right. If we look at that on our flow chart, pure matter, a glass of water, right? It's a compound because it's got different atoms in a fixed ratio. They're small, so it's molecular, and then those molecules are in turn made from H and H and an O, and that's where we stop, right? If I then took my hydrogen atom and split it into parts, I'd have a positive proton in the nucleus and a single orbiting electron, right? I took my proton out, and this is your extra credit homework, you'd find 3 quarks, right? If I take oxygen, if you look on the periodic table, oxygen's element number 16, so it has 8 protons and 8 neutrons in its nucleus with 8 orbiting electrons, all right? And then again, disassemble the protons and neutrons to subatomic particles, all right? But there, you know, so we take our atom, rip off the electrons of the orbiting, find the nucleus, there's protons and neutrons in a nucleus. If it's bigger than hydrogen, there's always neutrons. And then those can be broken down into quarks. Interesting. All right. Now, finally, not finally, summary. So atoms and molecules, and if you like ions too, which are just charged atoms and molecules, are microscopic, too small to see, right? But they're the fundamental building blocks of nature. Now, if you worked in Subway, right, Nature's Subway, and they said, make me a drop of water, you take an H, take an H, take an O, combine them to make a water molecule, and you do that. Let's do it, right? So 369, 369, 1,000 billion times, right? 1,000 billion times. Long day at work. Right, and that thing you make, that water molecule, is said to be macroscopic because you can see it. Now, if you think about it, that extends into our lab because whenever we do an experiment, by definition, we look at results with our eyes, right? So we see things that are macroscopic. Okay, but remember that macroscopic particle emerged because it was made from microscopic particles repeating their reaction many billions of times over, right? And that's the interesting thing about chemistry. We don't write the process over every time, we just write it once, which is called a balanced chemical equation. I'll show you in a second, and then just say, hey, repeat. Okay, so the official definition of what chemists do, okay, rather than have you think about that, I'm just going to write it. All right, I'm going to revert to my slide over here. So chemists, let me move this up. Chemists explain macroscopic phenomena, such as burning of, we'll look at this one in a minute, burning charcoal, that's a chemical process. Freezing water, that's a physical process. So we explain processes, right? We explain those properties of matter, right? We talked about. In terms of the repeated identical reactions of microscopic particles. Okay, atoms, ions, things like that. All right, that's kind of what we did here, right? So I said, hey, take an H, take an H, take an O, stick them together, you make a water molecule, right? So that's kind of a pseudo kind of balanced chemical equation. We'll do a real chemical equation in a second, which you've seen many times, but that's the concept, right? So I'm more about the philosophy than the nuts and bolts. All right, so let's talk about it. So this picture means, if you ever see this in the notes, this means that it's a relationship between macro and micro because that's what chemists do. So when you see this picture of me in 20 years, think about macro and micro, right? Okay. And a good chemist will always think about the macro in terms of the micro. That's how you know you've kind of crossed the border and moved into nerd territory when you start thinking about matter in terms of what it's made from in terms of atoms and molecules. All right, so let's explain what happens on your barbecue grill in terms of micro-macro expression, okay? So, in words, charcoal essentially is just pure carbon, right? But not diamond, it's graphite, right? Two different allotropes, if you remember that, all right? So carbon, solid, plus oxygen gas, here's a word equation, turns into carbon dioxide gas. That's interesting because, when we cook a burger, our goal is not to turn carbon into carbon dioxide. That's just a side effect of making a bunch of heat, right? So we burn things to make heat, but that burning process is itself a chemical reaction, which we can talk about what happened on an atomic scale, all right? So there's your word equation. So when I burn carbon, charcoal, with oxygen from the air, it turns into carbon dioxide gas. Now, when you really get into this, you like to think about what's going on in terms of pictures, right? This is what I think about. So if I think about what is carbon solid, well, if I zoomed in with an STM microscope on a kind of a brick of charcoal, now obviously the true brick of charcoal will be many billions of atoms, right? But here's kind of just a representation, right? So I've got 8 atoms of carbon in the solid form, meaning they're all stuck together. I'm going to put an asterisk next to that one because that's the one we're going to react, right? Okay, now remember, it's kind of a one at a time kind of process, right? So we'll react one of these carbons away, and this will just happen 8 times over to get rid of the brick. In nature, it happens 1,000 billion times to get rid of the charcoal brick. Okay, now oxygen gas, you may know, has a formula of 2 oxygens stuck together. O2, we'll see in a second, okay? And that will bump into that carbon atom, okay? So you get things hot enough, when they collide, bonds break, bonds make. We're not really sure, to be honest, because we can't film that, right? It happens on the femtosecond scale. Stuff goes in, stuff comes out, so we can see who stuck to who, but we just don't know how it happened, right? So what happens is, we're left with a 1 atom less block. Remember, this one's gone now. And where did it go? Well, it's stuck between those 2 oxygens, and off it went as carbon dioxide gas, right? Okay. We don't really think about that, because we just think about where the action is. Where's the action in that one process? Well, this carbon atom, right, and we go down here to write the kind of the balanced chemical equation. So if you've ever wondered what a balanced chemical equation actually is, it's a one-time description of what happens. It just happens many billions of times over. So this one, we represent as carbon solid. That's right, every time you write a formula in a chemical equation, it's a microscopic definition, right? Okay, so that's actually 1 atom of carbon from the brick, right? We reacts with 1 molecule of O2 gas from the air and turns into this molecule of CO2 over here. That's not your first balanced chemical equation, but it's probably the most philosophical, right? Okay, so remember, this is a microscopic definition. Multiply that, 10 to the 23 times, and you see the disappearance of a block of charcoal on your grill. Okay, and that's true for every chemical reaction, right? Happens 1 atom or molecule at a time, which we write down as a balanced chemical equation, and in our heads as chemists, we just say, oh, just repeat that a bunch of times, that's how nature works. Okay, hopefully that makes sense. All right. Now, that's the end of the kind of philosophical part of this, right? Okay, and now I'm going to get into the optional review stage. Before I do get into that, what I'm going to do is spring a pop quiz on you. Okay, attached to this Canvas post, right? So go to Canvas, it'll be posted, and if you can't get it, just drop me an email, I'll send you an attached document or something, right? I've got a little pre-test for you. Okay, now, it turns out that success in Chemistry 2, Chemistry 102, is really tied to how strong your foundation is from Chemistry 101. And that can't be overstated, all right? So what I'm going to have you guys do, without any preparation, and this is not going to be collected for grading, it's just for your assessment, right? I've got a little pre-test here, right? So print the pre-test out if you can. If you're unable to print it right now, just look at it on the screen and, write answers in a notebook, okay? And then grade yourself. This is a true, honest assessment of where you are in your general chemistry knowledge. You're going to find out, do I need help with Chemistry 101 or do I do not? Okay, most of you will, okay, and I want you to kind of prove it to yourself, all right? So let's look at the questions real quick and then I'll go through them. Well, all right, so just a few questions from General Chemistry 1. Print them out, try them, and then I'll go through them, okay? So I'm going to pause. I really want you to do it, okay? Come back when you've solved the questions and I'll go through them. All right, so I'm back, got my calculator. Okay, so these questions, hate to break it to you, they were taken from a Chemistry 100 syllabus, okay? So these are the simplest questions I could get. They're there to test basic understanding, okay? So as we go through, take that for what it's worth, right? So question 1, again, details are important, right? The reaction of P2O5, if you remember how to name that, diphosphorus pentoxide. The reaction of P2O5 with water, hopefully you know water is H2O, of course. To make, now, aqueous phosphoric acid, you have to know the basic chemical names and their respective formulas, okay? So phosphoric acid is the PO4 3- ion with 3 H pluses on the front, okay? That's aqueous. All right, so that's our unbalanced equation, right? And when you balance an equation, the simplest way to do it is to look at the lowest number atom first, if that makes sense. So 2 phosphorus there, so balancing an equation, I need 2 phosphorus over here, so I need 2 of these molecules. So as I like to say, hey, 2 cars with 1 phosphorus passenger is 2 phosphorus, right? 1 car with 2 phosphorus passengers is 2 phosphorus, right? Now you've locked in 1 molecule and 2 molecules, right? Now think about it. Oh, that's a 5, P2O5. When you think about it, right, the next easiest thing to balance is probably hydrogen. Yeah? Typically you'll save oxygen till last, so hydrogen on both sides has to be the same, right? So I've got 2 molecules with 3 hydrogens, so that's 6 hydrogen. The only place hydrogen appears on the left is here, so I need 6, so that's 3 water molecules. Okay, the oxygens now, 3 plus 5, 8, 2 4s are 8. There you go. If you've got 1, 3, 2 with the right formulas, yes, you have to give yourself a point, right? Okay. Next one, write net ion equation for the reaction between calcium chloride and potassium carbonate. Now, the net, if you remember, is the third of 3 equations in order. So I'll do the 3, right? So let's just do it. Calcium chloride, so calcium is a +2 ion, if you remember. Got to remember your ions and the charges. Chloride is a -1, and there's 2 of them. Plus potassium carbonate. Potassium's a +1. I like to do molecular ions in brackets like that. That's a -2, so I need 2 of them. Turns into, now when they swap partners, at ionic equations, they swap partners, double replacement. Calcium's going to go with carbonate. Luckily they're +2, -2, so it's going to be, that's chalk, that's a solid. We'll talk about solubilities in a second. Plus, well, there's 2 chlorides and 2 potassiums, right? So it's KCl is the name of the formula because it's the lowest ratio. And because there's 1, 1, 2, I need 2, 2, 2, 1. There you go. All right. Now, oftentimes when you have +1s, -1s, +2s, -2s in equations, that's the balancing numbers too, because the charges have to cancel, right? Now, how did I know that was a solid and the others were aqueous, right? Well, you have to look back at your solubility chart for that. Okay, now, I'm not going to get into the nuts and bolts here, but anything with carbonate, with a couple of exceptions, is a solid. Anything with a chloride, with a couple of exceptions, is aqueous. Okay, just have to review the solubility rules. All right, that's how we're able to assign state symbols. All right, now state symbols are super important in ionic equations because of what happens next, if you like. All right, so when I go to, that's the balanced. When I go to the complete, all right, complete is basically where the action is, right? So what do we see? So this aqueous means one of these things broke apart into its ions, right? So I've got 1 calcium plus 2 chloride plus, this breaks apart 2 potassium rather, 2 potassium, 1 carbonate. So if you like, I've broken it into its components. When you see aqueous, everybody in the car gets out, if they're ions, right? This is not dissolved, so therefore it doesn't break apart. This does break apart. Two cars with 2 passengers, so 2 guys, 2 girls, right? Okay. Now, the net, the thing thereafter, now that's actually where the action is. This is the complete description. This is the action, right? So what happened here? Well, you cancel spectator ions, right? What happened with what? Well, if you look at it, well, calcium hooked up with carbonate to make calcium carbonate. How we cancel things that don't react? Things the same each side don't react. Kind of common sense, really. Calcium ion plus carbonate ion turns into calcium carbonate solid. All right, if you got that, as written, give yourself a point. All right, grade it on the front. So far I'm 2 for 2. All right, next one, interesting. A couple of ways to do this. Now I teach it in a different way slightly than others, but it's the same mathematically, okay? So you can either do the chain method or you can do the table method or the grid method, which I like, okay? Now, I'll do both just because. Right? Okay, now 2 sodium hydrogen carbonate, which is baking powder, decomposes when you heat it to make water and CO2 in that ratio, right? So, question, what happens when 20 grams of baking powder is completely decomposed? What mass of product do I make? All right, so I like to do this, grams, molecular weight, moles, right? Okay, now I got 20 grams of this thing. I have to do lines here and grids. My destination is here, okay? To turn grams into grams, I have to go through moles, right? Because molecules react with molecules, not grams with grams, right? So that's my journey. And those are the 3 steps. If you do the chain conversion, which I'll show you in a moment, those are the same steps, right? Now the molecular weight, let's just work that out real quick. So sodium is 20, I remember the numbers, right? So sodium, this is just a rough calculation. 23 is sodium. I'm putting a molecular weight in this box, right? 23 plus 1 for hydrogen, plus 12 for carbon, plus oxygen 16, all right? 32, 48, plus 48. 84. 84 grams per mole. Now on a test, you do all the sig figs from the periodic table. I'm just doing it quick, right? So if we divide the go down, actually let's do this molecular weight here too. So 2 sodiums, 23 times 2, plus 16, 62. Okay, so divide the go down, grams divided by molecular weight is moles, right? So 20 divided by 84 equals, I think I had a bit of a, I have a voice activated camera, so sometimes I say a word and it does something. Okay, so just to recap that, divide to go down, I've got 0.238 moles of baking powder, right? 2 of these makes 1 of these. So I'm going to divide by 2 to know the number of moles of this I make, right? 0.119. Multiply to go up to get the grams of this one. So 0.119 times 62, 7.3. Yeah, 8 grams. So 7.38 grams, fair enough, right? Now, if I want to do that in the more traditional way, okay, I'll do it like this. 20.0 grams of NaHCO3. This step of the journey, right? Divide to go down, times 1 mole of NaH. Oh, wrong way. 1 mole of NaHCO3 is 84 grams. I'm just basically writing the molecular weight in terms of a fraction, right? So that's dividing to go down. Divide by 84, that's this step in a standard conversion, right? So grams is now turned into moles. Now this weird step here, right? 1 mole, 2 moles, I get it from the balancing, 2 turns into 1. So 2 moles of NaHCO3 turns into 1 mole of Na2O, right? So I'm just taking that number, divided by 2. So if I pressed equals, I'd have that number right now, right? But you know, with these chains, you just keep going, don't you? So I got the moles of Na2O, okay? So 1 mole of Na2O is 62 grams, multiply to go up, equals 7.38 grams. You know, sig figs would be 3. So if you have something close to 7.38 as an answer, doesn't matter which way you do it. If you took Chemistry 101 with me, maybe you did that. If you took it with someone else, maybe you did that. Doesn't matter, okay? I find a map easier than directions. That's what I'm saying. Okay, all right. That's that one. Now, turn this off real quick. Now, this one is a conceptual problem, right? So people always get confused, particularly in Chemistry 100, say, right? So how many apples in 1/4 of a mole of apples, right? Well, you know this, you know, and the mole is just a number, right? 1 mole is 6.02 times 10 to the 23 particles, right? If I'm counting apples, I'm counting apples. Okay, so it's just a conversion, right? So 0.25 moles of apples times 1 mole is 6.02 times 10 to the 23 apples. It's just basically 6 times 10 to the 23 divided by 4. All right, whatever that is, 6.02 divided by 4, 1.5. 1.5 times 10 to the 23 apples. Makes sense, right? If a mole is 6 times 10 to the 23, a quarter of a mole is 1.5 times 10 to the 23. Okay. Number, unit, 10 to the 23, give yourself a point. Okay. Now, oh, sorry. I just go through that again because I thought it was off the top of the page. So 1 mole is 6 times 10 to the 23 things. Those things we're counting are apples, right? So just common sense says, hey, if I want quarter of a mole, it's quarter of 6 times 10 to the 23, which is 1.5 times 10 to the 23. Just throw it into an equation. 0.25 moles times 1 mole is 6 times 10 to the 23. 1.5 times 10 to the 23 apples. Number in units important, okay? It's got to be the unit. Don't give yourself a point if you didn't put the unit. And 2 sig figs, because 0.25. Okay, finally. The number of moles of sodium chloride in quarter of a litre of 5.0 molar NaCl. Remember the golden rule, right? Moles equals CV. Maybe you got that from titration, right? I like to rewrite that as concentration is moles over volume in litres, right? That's what I like to do. Then if, you know, this is an old trick, right? If you just want concentration, it's moles divided by litre. Volume is moles over concentration. Moles is concentration times volume. So it's actually 3 variables, right, in a little triangle. All right. Number of moles, right? So moles equals CV, so it's the standard way to do it. Moles, now leave the units in, equals concentration, 5.0. Now M, remember, is moles per litre, times 0.25 litres. Leave the units in because they cancel. What's a quarter of 5? 5 times 0.25, 1.25. 1.3, 1.25. Let's see if we do it correctly. 1.3 moles. 2 sig figs. All right, so you've got 1.3 moles unit. Give yourself a point. Now, back to the front here. You know, ideally everyone would get 5, right? Does that ever happen? Once in a while, yeah, for sure. But most people, and you're looking at that saying, holy crap, I got 3, I got 2. Some people get 0 because it's been a while, right? If you're 3 or less from this test, which is just testing very basic concepts, you need to review Chemistry 101. No excuses, you need to do it, otherwise you're going to fail. And I'm putting that blankly on the page, right? Here's some statistics. Now, students follow me through from Chemistry 101 to 102. If you're one of those people, hello. Okay. And because I know the students, I'm able to keep track of their grades, right? So these are actual grades from previous students who've come through 101 to 102. Okay, now if you think about it, they have the advantage of knowing my style and how it all works before they even come in, right? So that's a little bit of an advantage for them. But then let's look at the numbers, right? So these are real grades, right? Had a B student get a B. I know that student. That was a hard-working, not a true kind of like, you know, kind of chemistry major, but someone who worked hard and wanted a grade, right? So they worked hard in 101, worked hard in 102, followed the script essentially and got the same grade. They did really well, okay? And the top A student in 101 is probably going to get the same in 102 because they're the A student, right? They work hard and they're motivated, probably chemistry the related field, right? But what's worrying is the others, all right? So I had an A student in 101 get a C, okay? I had a B student withdraw, that would have been a fail. A B student get a C and a B student withdraw, okay? So what you're looking at is usually if someone is just business as usual, right, it's at least a 1 to 2 grade point difference, right? So if you got a B, chances are, you know, if you just do what you did before, you're going to get a C or maybe like even a high D, okay? And that's the reality, okay? And this can be entirely traced back to the foundation of Chemistry 101, okay? You'll notice there are no C's on here. What about people who got C's in your Chemistry 101? Well, they all failed. Straight up, they all failed. I'm not saying it's impossible to pass Chemistry 102 with a C. It's happened before, okay? but you've really got to kind of rebuild that foundation in Chemistry 101. A C in Chemistry 101 kind of tells you there's some problems with the foundation. So if you've got a C in Chemistry 101, or maybe even a low B, you really need to go back and look at the Chemistry 101 stuff again, because it forms a foundation going forward. All right, okay. We are not in Canvas anymore. Canvas. We're not in Kansas anymore. That was interesting. Okay, bottom line is, folks, it's not business as usual. This is the common mistake people make in chemistry, right? It's not modular. Think of Chemistry 101 and Chemistry 102 as the same course that just lasts over 2 semesters. It's not like you can just put this in a box and forget about it. What you did last semester, if you took Chemistry 101 or before, whenever it was, you need to have that stuff at your fingertips. If it's not, this happens, right? Okay, so it's not like a new module. It's not all kind of like separate by itself. It relies heavily on what went before. Okay, now, this is something a little, if I can find it, it's something a little cheesy. This is a thought I just leave you with. Right? Don't get into denial, all right? Don't get into denial. There's a picture of the River Nile, right? And there's my cheesy comment. Denial isn't just the river in Africa, right? So if you just think, it doesn't mean anything, you know, I got a C or a low B in 101, I'll be fine. No, you won't. You gotta do the 101 stuff. And I'm gonna turn it into a separate video. I've gone on long enough with this one. So what I'm gonna do, I'm gonna put a separate review video up, which will follow this one immediately. Fine, if you got 4 or 5 and you feel comfortable with your 101 stuff, you don't have to review, okay? If you're in the 3 or less range, you need this, okay, that you need this. And we'll talk more about strategies for that in the review video. All right, I'll stop now and I'll see you guys on the next one.